So we come to the final topic that we'll be covering in this course, and that topic is randomized computation. This, I would argue, is one of the most important developments in computational complexity that has gone on to affect things just beyond things within theory and has a lot of impact in computer science, which is the notion of randomized computation. So these are algorithms that flip coins. Now, the best introduction to randomized computation is through an example, and I'm actually going to start with the classic example of a randomized algorithm, and this is by Soloway and Strassen in 1977, and they were considering an extremely important language both from a mathematical perspective and, with the advent of cryptography, a very important practical problem, and that's a language called primes. So primes is essentially the language of all integers, positive integers, so that n is a prime number. Now, what is important is that the size of the encoding in binary was basically log base 2n. So we want an algorithm that determines if n is a prime number, that runs. So a polynomial time algorithm is one that runs in time polynomial in the encoding size, which is polynomial in log n, that runs in time polynomial in log n. Polynomial in log n. And so I'm going to give you the algorithm by Soloway and Strassen, which was, and there was another algorithm given by Miller, by Rabin and Miller. There's a Miller-Rabin primality test, and those actually form the real procedures that people use when they want to determine if a number is a prime number. And this is a randomized algorithm. So there's some amount of number theory background that is required to prove everything, which I'm not going to get into. So I'll just give you the high-level idea and how randomization plays a role. So there's something in number theory known as the Legendre symbol. And so let's consider an odd prime p. That's just any prime that isn't 2. And any a. And for simplicity, I'm just going to assume that a goes from 1 to p minus 1. This allows me to sort of get rid of certain cases. So the Legendre symbol, which is actually written as follows, it has somewhat of a funny definition, and this is known as the symbol for quadratic residue. So what is a quadratic residue? Actually, the quadratic residue definition is here. So it's plus 1 if there exists a b such that b square is equal to a mod b. Okay? And it's minus 1 otherwise. And so this is actually technically, this is called a quadratic residue. So this checks if A is a quadratic residue modulo B. So is there some, it's like saying, does A have a square root in modulo P? Okay. And so there is a theorem, and I guess this is also related to Fermat's little theorem, which says that this symbol is equivalent to A to the P minus 1 divided by 2 modulo P. So this is, again, for all odd primes P and all, I mean, technically this is even true for all A, but one has to redefine things, and so I'll just stick with this. So this is a property that all prime numbers have. So if you fix a prime number, then for every A, the following property will hold. This theorem will hold. But you're given a number n, and you want to determine if it is prime. So what is interesting is there is something called, the generalization of this is called the Jakobi symbol. And so the Jakobi symbol, often written in this form. So now again, n is an odd number, not necessarily prime. And A will range from 1 to n minus 1. And it generally works for all n in the modulo space, but there's no need to get into that. And this is essentially the product of all A over P to the EI, where n is equal to the product of PI over EI. So it's overall I over here. So what this means is that this is the prime factorization. So if you take the prime factorization of a number, then that's equal to, by the fundamental theorem, in number theory, by the prime factorization theorem, every number can be expressed as a product of prime powers, and you essentially take the corresponding symbol over here. So note that the Legendre symbol is basically plus 1 or minus 1, and therefore the Jakobi symbol is also plus 1 or minus 1. So it's just plus 1 or minus 1. This is a lot of beautiful work of essentially of Gauss. Show that there are efficient algorithms to compute the symbol. The symbol looks like such a strange quantity. Of course, here there is a way of computing it. For the Jakobi symbol, you think, how would one even compute such a thing? And so there's a remarkable lemma. Well, there are two lemmas, which say that this Jakobi symbol can be computed in O of log A times log n. So essentially in polylogarithmic time. And an even more interesting lemma says that if n is composite, so if n is not a prime, then for at least n over 2 values A going from 1 to n minus 1, the Jakobi symbol is not equal to A to the n minus 1 divided by 2 mod n. So this is what it says. It says when P is a prime, then this symbol, and the symbol is quadratic based on quadratic residues. Ignore that for now. If you're not familiar with this, it's just some number that you can compute, and that number is the symbol is going to be plus 1 or minus 1. That's it. And there is a polynomial time calculation that gives you whether it's plus 1 or minus 1. So this theorem actually fails for half the values of A if n is composite. Okay?
So if we choose random values of A, then each of them has no more than a 50, and supposing it is composite, there's no more than a 50% chance that the test will lie to us.
Exactly. So now I'm going to write down what the primality test is. Okay, and this is called the Soloway-Strassen primality algorithm. So here is the primality algorithm. So the input is n. So the first step is to pick a, I'll say, uniformly at random. It's called UAR. By the way, there is something that I should have qualified here. That this formula is only true if the greatest common divisor, the GCD of A and N, is equal to 1. Meaning that A and N are coprime. But if A and N are not coprime, then the symbol is usually defined as 0. But if you find an A that is not coprime with N, then you know that N is composite. Okay, so this is only defined if the GCD is 1. Should have clarified that. Okay, so pick A uniformly at random in 1 to n minus 1. And if the GCD, the greatest common divisor of A and N, is not equal to 1, then go ahead and reject. Otherwise, compute the Jakobi symbol. Compute A to the n minus 1 divided by 2 modulo n. And finally, if the Legendre symbol, the Jakobi symbol, is not equal to A to the n minus 1 divided by 2 modulo n, reject, else accept. Okay, so how long do these steps take? Okay, so let's think about this. Let's think about it a little carefully. So note that n, I'm going to say n is equal to log base 2 of n, because little n is the size of the representation. Now this can be done in O of log n. You just pick O of log n random bits, right? You just guess the bit representation of a number. What about computing the GCD? If you use Euclid's algorithm, then you can do this in polylog n time. I believe probably log squared n, or correct me if I'm wrong. Polylog n time. As we said, there is an algorithm to compute A to the n minus, the Jakobi symbol. To compute this quantity, you have to do some tricks. You have to do some powering, right? You have to basically compute a power of A. But all the numbers are all log n bits. I'm sorry, not log n. This is my apologies. This is just O of n, right? Sorry, my apologies. It's polynomial in n. Right? And this can be also done in polynomial in n time. The computation of this one has to be a little careful. I mean, it can be done. But remember that even though A to the n minus 1 divided by 2 may be a huge number, it's all done modulo capital N. So you can keep reducing it modulo capital N, and therefore your numbers won't be small. They'll be efficiently representable. And so this gives a poly n, which is a polynomial in log n time algorithm. Now, what are the guarantees of this algorithm? So if capital N is prime, then this always accepts. Why? The GCD will always be 1, right? It's picking something from 1 to n minus 1. If n is prime, then it is co-prime with every number less than it. So it's never going to reject there. And by the theorem we stated earlier, we know that the Jakobi symbol, which will actually be the Legendre symbol, is equal to a to the n minus 1 divided by 2 modulo n. So it always accepts. Now the interesting case is if n is composite, it rejects with probability at least a half. Or the way I'm going to write this, I'll say that it accepts with probability, that's WP, at most a half. So this algorithm is very different from all the algorithms that we've seen, and maybe from all the algorithms that you've seen so far, maybe not even in this course, in courses like 101 and 102. There is some probability of making a mistake. So the algorithm can error. Now what we can do is we can boost the success probability. To boost the success probability, what we can do is run k independent instantiations of the algorithm. Okay. If all runs accept, then accept. Else, reject. Now we know that if n is a prime, the algorithm never makes an error. The algorithm always accepts as it should. But if n is composite, it makes an error with probability at most a half. But if you run it k times, the probability of making a mistake in all the runs is going to go down exponentially in k. So let me write this as, suppose n is composite. So this is the probability that all k runs accept. So what is this probability at most? Each run accepts with probability at most a half. And you did k independent instantiations. What is the probability that all of them accept?
Is it 1/2 to the k?
1/2 to the k. So it's 1 divided by 2 to the k. So you see that the error goes down exponentially. In other words, the probability of an erroneous answer that's really small. So if you ran it 100 times, then the probability of error is probably less than maybe the number of protons in the universe. 1 divided by the number of protons in the universe. Right? Just run it. You ran it 50 times, it's enough. Right? So the error probability is really small. And indeed, if you were to go and pick up a package which exists, or I think even Java has a function that tests primality. Like you give it a number, it tells you whether it's prime or not. It has an error, but the error probability is so small that it's probably lower than the error that a cosmic ray is going to hit your machine and flip a bit. You can get the error to be extremely small pretty quickly. So this is a randomized algorithm. There's an additional point that is worth making here. That when the algorithm rejects, says n is composite, it outputs a certificate, right? And that certificate is A. The certificate is that number A that was discovered, because you know that if there exists any such A where the step 4 rejected, then you know that n is not a prime by this theorem that I described earlier, right? We have this theorem earlier. We have a theorem earlier that says if P is a prime, then the Legendre symbol is always A to the P minus 1 divided by 2. And therefore, when the algorithm rejects, it actually provides a certificate of rejection. It outputs a certificate. Right? So this is looking like co-NP in that sense. And we'll see that there is a relationship. But when it's in the language, it always accepts. When it's not in the language, the probability that it erroneously accepts, we said was at most a half, and we agreed that we could even get it down to 1 over 2 to the k with k independent runs. And when it rejects, it provides a certificate. So this is a very, even though you may not have followed all the number theory behind it, which is actually quite beautiful, and it's not, you can read it up, it's very nice. The important thing is to observe these facets of the computation. It's not just if it's in the language accept and if it's not in the language reject. It's much more nuanced now. If it's in the language, it accepts. If it's not in the language, it actually accepts with probability at most half, but it's at most half. So in other words, the error is less than probability half. So any questions about this? Any questions?
So this isn't the same algorithm that was discovered, because we said earlier that there is an algorithm for factoring primes, right? That is wasn't that discovered like sometime in the last 20 years or something?
Yeah, so that actually proves, okay, so good question. So I'll come back to that at some point. This is a randomized polynomial time algorithm. And what Agarwal, Kayal, and Saxena in 2003, 2004 discovered is a deterministic polynomial time algorithm.
I see.
They actually showed that the language of primes, they showed that this language primes is actually in P. They gave a polynomial time algorithm. This is a polynomial time randomized algorithm, and this was given in the 70s.
I see. Gotcha.
But this was one of the first instances of a randomized algorithm of this form. People had used randomization for computation back in the 50s with Ulam in doing what's called Monte Carlo simulations. But this was one of the first instances where it was used in a very different way. And there was this notion of deciding a language except with some error. And so now what we're going to do in this lecture is we will formalize that and define complexity classes.
Interesting.
Okay, questions? Okay, so there are multiple definitions, or I guess they're all equivalent, but I'm going to give you one definition of a probabilistic Turing machine, which I think is sort of the most, is the clearest one to understand. There's also one in terms of probabilistic transition functions, but I feel that this is better. So what is a probabilistic Turing machine? A probabilistic Turing machine has an extra tape of random bits. So each cell has an independent It's an independent, unbiased 0, 1 bit. This is also referred to as a Bernoulli. So the way you should think of it is, here's your machine M. So this is X, and this is the usual input tape. This is the random tape. And it's convenient to think of the random tape as read-only. So it's not using this space for writing, although for our purposes this is not really going to make much of a difference. And so what it has over here are just a sequence of bits. And what you can think of is, the head over here is reading these cells. Every time it reads a new cell, poof, something flips, and then you get a random bit. So the random tape is read-only. And we will refer to this as R. Once you fix the input and fix R, M is just a normal deterministic Turing machine. The only difference is that M gets an additional input. So M gets, one can almost think of it as an input, gets an additional input of random bits. And this is also called the random seed. So in addition to its input, it gets a random seed. So technically M is a function of X comma R. M runs both on the input and takes sort of a secondary auxiliary input, which is the randomness. So what does it mean for M to accept X, which is ill-defined? MXR will either accept or reject. Because at this stage, one can now think of M just as a deterministic Turing machine, where M is a standard deterministic Turing machine, which just takes two inputs as opposed to one. What we can look at, the following. So fix input X, and we ask, what is the probability? What is the probability that MXR accepts? Now this is the probability over the choice of R, of the random seed. So what you can do is, you can imagine you fix your X, and then you just keep changing R, and you run it. And you're looking at the probability over that space. What is important to note is that the probability depends on X, but the probability doesn't depend on R, because it's the probability over R. So for any input X, what is the probability over R that MXR accepts? This can be a little confusing the first time you see it, because you might think of there being a probability over the input, which there isn't. There is a probability over the randomness that the algorithm uses. And it's easiest to think of the randomness as being a separate seed that is provided to the algorithm or the Turing machine M. Okay? All right? Any questions about that? So now let us define randomized computation in terms of languages as we've done with, P, NP, P space, so on and so forth. So I'm going to define now a language L is in Bp time T of n. So what is Bp time? That's bounded polynomial time. If there exists a probabilistic, which I will also refer to as a randomized Turing machine M that runs in time T of n and satisfies the following. So for all x, right? For all inputs x, I'll just write it as x is an L. X is an L implies that the probability over all random strings. So what is the length of the random string? The length of the random string is at most the running time, because it has to read those bits. So we can just say that the length of the random string is at most the running time. The probability that M X R accepts is at least 2/3. When X is not null, the probability that M X R accepts is less than equal to 1/3. The important thing is there is a gap. It's 2/3 versus 1/3. So what is interesting is that for all inputs, the probability that M X R, so it's the probability over R, accepts is either more than 2/3 or less than 1/3. It's never, so there's a gap. You can think of it as, if I'm just writing out the probabilities here, if the probability is 1/3, 2/3, this is accept and this is reject. The probability will never lie in between 1/3 and 2/3. That's the definition. That's the definition of Bp time. This is the definition. It says that there is a probabilistic Turing machine with the guarantee that if X is in the language, its probability of accepting is more than 2/3. If it's not in the language, the probability of accepting is less than 1/3. Okay, and let me just keep this definition up here. Keep this definition there. And BPP, which is bounded probabilistic polynomial time, which is like it's like the bounded probabilistic version of P is, as by now is just you're looking at all polynomial time Turing machines. Polynomial time randomized Turing machines with this property, the language is accepted by them. This is BPP. Bounded probabilistic polynomial time. Any questions about this definition? It's a bit to take in, so pause here and take any questions.
So is the 2/3 and the 1/3, is that just a factor of the polynomial, or would it be different if we said exponential time or something like that, or linear?
You mean why did we make this 2/3 and 1/3?
Yeah, is that specifically for polynomial for BPP?
No, it's a good question. So as we will show later on in the lecture, we have a lot of flexibility with those constants. These are only of this is just for convenience.
Oh, okay.
If you replace this with 3/4 and 1/4, you will have the same complexity class BPP.
Oh.
So BPP doesn't depend on the actual constant. Indeed, there's going to be an immense amount of flexibility in what you can have. The only important thing is there is a gap.
Okay.
So you want there to be a gap between rejecting and accepting. And what we can do is something called boosting to actually, we can kind of spread that out so that the gap is huge.
Gotcha.
And this is a very important point that we will discuss. Why 2/3 and 1/3? And this is only a matter of convenience that we use 2/3 and 1/3.
So if I understand correctly, the gap is actually put in there because essentially, and we can quote unquote boost a language. I don't know the actual definition of it, but what I'm assuming it is, I think, essentially if it has any probability other than 1/2, right?
You need a gap, exactly. So what we'll show is that even if that gap is really small, as long as the gap is at least an inverse polynomial, we can boost it out and we can get it to whatever we want.
Okay.
We'll see that, and it's a non-trivial fact. It's a consequence of something called, the Chernoff-Huffington Bound in probability theory. So we'll see that. What's important to note is that the probability being, you can always get the probability of accepting to be half, which is to simply guess randomly, and you'll be correct with probability half. Right? Which is like, as they say, like, a broken clock tells time, twice a day. So you just guess randomly, and with probability half, you'll be correct. So half is not interesting. And so the question is, how much away from half can you get? And it says, as long as you can just get up to 2/3, and we'll see that, that this gap can be amplified significantly. Okay, so does this definition make sense? Okay, so this is BPP. Now there is another class called RP, and this is called randomized polynomial time. And so this has what's called one-sided error. It's called one-sided error. So what does one-sided error mean? So note that here it can make errors on both sides, but our primality test was always correct when it was in the language. This is actually going to be the opposite of that. So what it says is if x is in the language, then the probability that MXR accepts is at least 2/3. But if x is not in the language, the probability that MXR accepts is 0. So what this is saying is if x is not in the language, it will never accept. But if x is in the language, then it may make an error.
Would co-RP be the opposite case?
Exactly.
Right.
So yes, that is exactly what I was getting to, which is co-RP is just saying the opposite. It would say that if x is in the language, the probability that MXR accepts is 1. And if x is not in the language, then the probability that MXR accepts, I'm just going to put the constant, I'm just going to say less than 1/3. It turns out that again, the 2/3 and the 1 There's a lot of flexibility in choosing that. These are merely conveniences. And in this case, as long as you have anything that's less than 1, that's good enough. Because you can just repeat it a bunch of times. Like as we saw. You can always do this repetition, the independent repetition. So you could even make this 1/3, you can make it 2/3, it doesn't really make a difference. What I want to say over here, another way of interpreting this, which is going to be important, is that when the M accepts, it provides a certificate. And the certificate is the random seed. So let's just say you ran it and it accepted. You know that it can never accept something that's not in the language. And so the random seed is the certificate. And that certificate is the random seed. Because you know that there is no certificate, there is no random seed that can make it accept if it wasn't in the language. And similarly over here, when M rejects, it provides a certificate. All right?
I guess a common thing that we might think about for these different language classes and whatnot is the intersection.
Yes.
And in this case, the intersection of RP and co-RP would just be a deterministic algorithm, right?
Good.
Well, at least it doesn't care about the certificates.
Not entirely, but the thing is, that's a good question. So what happens in the intersection? So good. So at this point, I'll just write down a few things. You know that P is certainly contained in RP, and RP is contained in NP, and P is contained, I'll say, is also contained in co-RP, which is contained in co-NP. BPP is a lot more unclear what's going on with BPP, and we will come back to what's going on with BPP. And indeed, RP union co-RP, like all of this is contained in BPP. And clearly BPP is contained in P space. Because in polynomial space, you just simulate all the randomness. In BPP, in P space, you can just simulate all the randomness. Okay, so I'm now going to define something else. So this is RP is randomized polynomial time, which means it makes errors when X is in the language. Co-RP, it makes errors when X is not in the language. And this was the primality algorithm. Now I'm going to define something called ZPP, which is actually called zero error probabilistic polynomial. So MXR never makes an error, but the running time is a random variable. So this is a Turing machine that you don't have a bound on its running. It might run forever. It may actually not even halt, but the running time is a random variable, and the expected or the average running time. So I should say for all X, for all inputs X, the expected running time is polynomial. So this is like randomized quicksort. If you think about randomized quicksort, it never makes an error in the output, but the running time is randomized. And that's what ZPP is. ZPP is zero error probabilistic polynomial, Never makes an error, but the running time is a random variable. And this is, this is not an obvious statement, but you can actually prove that ZPP is equal to RP intersection co-RP. Okay, so just to draw a picture, here's P. That's ZPP. And that's RP. So there's actually nothing there. So this is co-RP. The intersection is entirely ZPP. And all of this sits in BPP, which sits in P space. RP is contained in NP, co-RP is contained in co-RP, and you can ask, what about BPP versus NP and co-NP? And that's something that we may get to in the next lecture. So these are the basic classes that we're going to talk about. This is not hard to prove, but it requires a little bit of probability theory to prove it. Like basic, you just need some basics known as the Markov inequality, and you can prove that ZPP is equal to RP intersection co-RP. I can even tell you how it works. What you do is, if you have an RP machine and a co-RP machine, you keep running them in parallel until one of them gives you a certificate. Right? So you can run the machine in parallel until one of them gives you a certificate. And so if X is in the language, if you keep feeding it different random things, eventually it's going to give you a certificate. And then at that point you stop and And if X is not in the language, well, eventually when it rejects, it provides a certificate. So it's just it will keep running, and at some point it will provide a certificate.
I would presume that the running time being the random variable may be arbitrarily long, but presumably the measure of the cases where its runtime is infinite should have a measure of 0, I presume.
Yeah, another way of putting it is that the runtime is it's going to sort of decay exponentially. So the average is going to be essentially so you can ask, how many times do you need to run these machines before you eventually hit it? And on the average, you can argue that the expected number of runtimes is constant. So what that does is that basically tells you that ZPP, let me see if I'm getting this the right way. So that tells you that ZPP contains RP intersection co-RP. And to argue that ZPP is contained in RP or co-RP, you can imagine just taking your ZPP machine, and if it runs for too long, you just stop and give a default answer. If your default answer is yes, then it's RP, and if it's no, it's like co-RP. So that's basically how it works. Okay, any questions? Okay. So now what we'll discuss is an issue that has been raised, which is the robustness of Bpp, or Y 2/3. And if you ever get a little deeper into theoretical computer science or randomized algorithms, you'll see this 2/3 popping up a lot. Like everybody uses 2/3. And it's just become a convention. There's nothing sacrosanct about actually using 2/3. What's important is that it's strictly more than a half. Okay. So let's fix some language. So L is in BPP, right? So we're looking at some L. And for convenience, I'm just going to say let L of X actually be the function, the indicator function. 1 of X is an L, 0 of X is not an L. And I'll just say that mxr is equal to 1 if mxr accepts, and 0 if it rejects. Okay, so what is BPP? BPP is just saying for all x, the probability over the randomness that mxr is equal to lx, this is at least 2/3. It's just saying that the probability that it's correct is at least 2/3. So you can say, why not something else? And what we'll see is we'll just write this as half plus epsilon, and the epsilon is 1/6 here, right? Because half plus a sixth is 2/3. So you can think of it as, if I were to define the class this way, then I would say this is BPP 1/6, where the error, or the, I'm sorry, not the error, but the gap from a half is 1/6. And what we'll show is that for all constant c, BPP of actually 1 divided by n to the c, like this is really small, is the same as the BPP with doing 1/6, and is actually the same as BPP of half minus, I mean, it turns out to be, 2 to the minus n to the c. So I'll make this clear. What this is saying is that you can get the error to be exponentially small, like a tiny error. Okay. So let's step back for a second. BPP 0 is sort of trivial. Like, contains all languages really, because for any language, the Turing machine could just flip a random coin, right? So in some sense, the probability of r mxr being equal to L of x being a half, or at least a half, this is trivial. Just flip a random coin and output. And your probability is going to be a half of guessing correctly. So it's only interesting when it's half plus epsilon for some epsilon that's non-zero. So we'll prove our theorem here. We'll say, suppose m is a probabilistic polynomial time dm such that for all x, the probability over the randomness that mxr is equal to, so I'll write it this way, L of x is at least half plus 1 divided by x to the c. So c is some constant. Right? This is saying that the error, or rather the probability that it's correct. So if it's doing half, that's just guessing randomly. It's doing a little better than a half, but polynomially small, bias in the right direction. If this quantity is 1, then of course it's deterministic. It's not a probabilistic Turing machine because it's always doing the right thing. Or at least if the runtime, imagine that the runtime was fixed. Right? If it's, or maybe the way to say is if this was 1, then this is like ZPP. So in this case, what we're saying is consider a machine which is correct with probability half plus a little bit more. Then, for all constants d, there is a probabilistic polynomial time Turing machine M prime, which is again the same form, such that for all x, the probability over R that mxr being equal to L to the x, this is going to be at least 1 minus 1 divided by 2 to the x to the d, which is, it's exponentially small, the error. So we're able to get the error. So another way to think of this is you start with, okay, so here is half. And so this is, initially this is what you have, accept and reject. Right? This is saying that the probability of accepting is here. So that's why it's half plus this, right? That's the probability of being correct. So this, the gap over here is really small. It's 1 divided by, I'll say n to the c, where n is the size of x. From that, we can actually get something that looks like this. It's almost like, it's not deterministic, but it's sort of so close that the acceptance probability is here, the rejectance probability is here. And this is really, really tiny. 2 to the n to the d. Okay, we're able to basically boost the probability of success. And indeed, this is one of the reasons why randomized algorithms are so powerful. Because the moment you're able to get sort of an answer just in the correct direction, just a little bit, then you can boost it to get something that is correct with overwhelmingly large probability. So much so that the probability of error of a randomized algorithm is less than the probability that your hardware has an error. Right? The probability of error is so small that it's less than the probability that there's actually an error because there was a hardware glitch. You can make it 1 in a million, 1 in a trillion by boosting fairly efficiently. Does this theorem make sense? Okay? So now let's give the proof of this theorem. Now the algorithm may not be, would be something that you've guessed. So let us describe this machine M prime. Okay? And so what it's going to do is it's going to run k independent invocations, or you can think of it as copies of M. I haven't told you what k is, and actually that's where all the magic is going to lie. I'm going to choose k appropriately, but for now, you're going to run k independent copies of M. Okay? Now, each will either accept M, accept X, or reject X. So I'm thinking of the input, I'm just fixing it as X. You run k independent copies of M. Now each of these copies is either going to accept the input or it's going to reject the input. Go by the majority vote. If more than half accept, accept. Else, reject. So if more than half of the runs accepted, then M prime will accept, otherwise it will reject. Now this is similar to the RP, actually the primality argument, but there, it was sort of, you knew that when it rejected, it gave a certificate, so you could just stop. But here, because you have error on both sides, you just run many copies, and then you take the majority vote. How large should k be so that the probability of error is less than 1 divided by 2 to the x to the d. So this is the question that we need to address. So what's important to note is you can get exponentially small probability by only running it with a polynomial overhead. Okay, so let's sort of write this out. So when x is an L, and I'm just looking at the machine M, the probability that mxr, okay, this is the machine, mxr is equal to 1, meaning that it accepts. This is at least half plus 1 divided by x to the c. And I'm going to refer to this quantity as epsilon. So I'm going to call this as epsilon. This is half plus epsilon. When x is not in the language, the probability of r that this is at least is at most half minus 1 divided by x to the c, which is half minus epsilon. So what I want to think about is really each running of m for a choice of r. So you choose r at random, you run m, and either it gives you 1 or 0. Right? It's either 1 or 0. So think of this as a coin. So we can think of this entire box M. So you fix R. I'm sorry, fix X. So this is fixed. R, this is random. Both of these are being fed. And it outputs either heads, which I'll think of as a 1, or it outputs tails, which is 0. So if you fix X, you can think of this entire box, this is just a coin flip, but a biased coin flip. What do I mean by that? When X is an L, if I just step away and look at the box, I can treat this as a coin whose heads probability is half plus epsilon. If X is not in L, then this is a coin whose heads probability is half minus epsilon. Right? So you have this hidden coin, and I promise you, either the heads probability is half plus epsilon, or the heads probability is half minus epsilon. And your job is to tell me which one it is. All you get to do is flip the coin, and you can see what happens. Okay, does this make sense? I give you a coin, and I promise you that the heads probability is either half plus epsilon, at least half plus epsilon, or it's at most half minus epsilon. But you don't know which. You don't know which. And your job is to find out which by basically flipping the coin enough times. So what are you going to do? You're just going to flip the coin many times. And if you see more heads than tails, you say it's more likely to be in the first case because the probability of heads is more. And if you see more tails than heads, then you'll go with the opposite. How many coin flips do you need to do to be confident of your answer? Obviously, if you do one coin flip, you're not going to be that confident. You could have a lot of error. What about 2? What about 3? If you did 100. So you have to understand how the probability is you need to understand the probability of error as a function of coin tosses. And naturally now you need tools from probability theory to answer this question. Okay, at this point I want to stop and I want to make sure that you understand this logic. So please ask me questions if there's any doubts about this. All right, so this is clear. Distinguishing. So it boils down to this game of distinguishing between coin with a heads probability of greater than half from a tails probability of, with a heads probability half minus epsilon. Now, if you've ever heard of something called the central limit theorem, what we actually have to use is some kind of quantitative version of the central limit theorem. And what the central limit theorem says is that if you did lots of coin flips going to infinity, the fraction of heads that you'll see in the first case is very close to half plus epsilon. It's not going to deviate much from a half plus epsilon, the fraction. So the fraction of heads in the first case is going to be very close to half plus epsilon. The fraction of heads in the second case is going to be very close to half minus epsilon. And because there's an epsilon there, the half plus epsilon and the half minus epsilon are apart, you can start distinguishing these cases. When you do, now central limit theorem says if you do infinitely many coin flips, you will know the answer. And you need a quantitative version that tells you, well, how many do you really need to do before you get answers with some confidence? And so what we need to do is use something called the Huffington Bound. Or there are various versions. There's also called something called the Chernoff bound, but I'm specifically going to use the Huffington bound. So I want to spare you some of the details of the exact statement of the bound, and instead give you sort of a high-level picture. So let's just say that suppose X is an L. Suppose X is an L. Run k times. We expect at least k over 2 plus epsilon k heads, which is the same thing as that many acceptances. At least k over 2 plus epsilon k, because it's a half plus epsilon. So you expect, that is the expected, the average number of heads is at least k over 2 plus epsilon k. And so you can say, what is the probability that the number of heads is actually going to be less than k over 2, which is when it would lose the majority vote. This is losing the majority vote. Or maybe I should technically remove that equal to sign there. But it's all the same. Whether you make it equal to or not doesn't make a difference. And this turns out to be, so the Huffington bound tells you that this is going to be exponential in minus 2. I'll write this here. The deviation squared divided by k. So what is this saying? It's saying, look at the deviation from the expectation. It is going to be exponentially small in the deviation squared divided by the number of trials. So what this means is, as you increase the deviation, your probability is going to go down. Likelihood of deviating more and more is going to go down. Okay? So what you get over here is, what is the deviation? The deviation is the difference between this. The deviation is basically is at least epsilon k. So this is just saying this is how much you expect minus k over 2 what you see. The deviation is the difference between what you expect but what you actually saw in this case. And so this deviation is epsilon k. And so you kind of plug that bound in over there, and this is 2 epsilon squared times k. And the k cancels out. So the probability is 2 epsilon square k. And so now what you can get is epsilon was 1 divided by x to the c. If k is set to be, essentially you can set it to be epsilon squared, so this 2c times x to the d. Okay, so this is basically x to the 2c plus d. So this is just some polynomial. So you run it a polynomial number of times, then the probability that the number of heads is less than k divided by 2 is at most exponential 2 to the epsilon square times k, which is x times 2c plus d, and you work this out, and this will be at most exponential in minus x to the d, which is what we wanted to show. So this is the probability of error. If x is an L, the probability of error is at most exponential in minus x to the d. And if x is not in L, you can basically run a similar argument. You use the Huffington Bound again, and you have to look at what is the probability it's going to be more than k over 2. In the other case, you expect at most k over 2 minus epsilon k heads. And you have to look at the probability if the number of heads is more than k over 2. But the math is actually identical. The Huffington Bound looks the same on both sides. Both the upper and lower tail bounds are the same. And so if x is an L, the probability of error is exponentially small, which is what we wanted. Okay, so this is sort of the argument. I mean, you have to use the Huffington Bound, which is not something that that I would expect you to know at this point. But this is just to give you a basic feel for what's going on. You have to understand this probability of flipping k coins and seeing how many heads there are. And you use bounds that give you these are called tail bounds, that tell you what is the probability of deviating from the expectation. Okay, so this is quite a bit. So any questions? I'll pause here for a few minutes and take any questions that you have.
So the part where we use the Huffington Bound was when we said that that the probability of the number of heads being less than k over 2 is less than that exponent, right?
Yes. This is the Huffington Bound.
Okay. Gotcha.
So another way to think of the Huffington Bound is to say the following. So this is also called a binomial tail. So let's say you have a coin. Let's take the simplest case. You have an unbiased coin, which means the probability is heads half, tails half. You flip it k times. You expect to see k over 2 heads. What is the probability that you're going to deviate significantly from k over 2? And that's what the Huffington Bound tells you.
I see.
Except in this case, your coin is biased. It's biased in a particular direction. What is the probability that when you flip things, you'll still see the bias? Like, what you want is to see the bias. So how many flips do you need to do so that you can reliably see the bias? Where this is like the reliability, the error. So the error is so small, so you will see it with overwhelming probability, you will see the bias. What does it mean to see the bias? It means that you will determine that the probability is more than a half, which is what you wanted to do. Because the moment you can distinguish whether it's more than half or less than half, you kind of separate. You separate the x is an L from the x is not an L.
Right, because the bias ultimately determines whether the string was an L or not.
Exactly. So the bias tells you whether it's an L or not an L. And so your job is to determine if this coin is biased towards head or biased towards tails.
Sure.
And so the number of flips is going to depend on the bias. But now, is it depending exponentially on the bias or polynomial? And it turns out it depends actually polynomially on the bias. You only need to pay 1 divided by the bias squared. If you think of epsilon as the bias, what it says is if you do 1 divided by the bias squared, then essentially it starts converging extremely rapidly. And it's exponential. beyond that. What's important is that it's exponential, and this is going to be used heavily in a bunch of theorems that we will prove about BPP. Is that you can get the probability of making an error to be exponentially small in the length. Okay, questions? All right. So this is a very important aspect, which is the robustness of BPP, right? Which tells us that the 2/3 is a matter of convenience. But what it also tells us is that we can replace the 2/3 with essentially 1 minus something exponentially small, and this will be very helpful in proving a collection of theorems. So instead of, I still have about 15 minutes left, but maybe I don't want to launch into a new theorem. Let me sort of tell you, what are the theorems regarding BPP that we know. So let's go back to this. We've got all of this. So for RP and co-RP, it seems that we have some kind of understanding. Just almost by definition, RP is in NP, co-RP is in co-NP. But what about BPP? I mean, can we say anything better than it being in P-space? Because that seems like too much. I mean, P-space, you can simulate all the randomness. And in BPP, you're basically just saying that the bias is, it's 2/3 versus 1/3.
I'd say it's in sigma 2, or like sigma 2 set.
Yes.
Like in the polynomial hierarchy.
Yes, so we can say it's in the polynomial hierarchy. It's a non-trivial statement, but that's exactly what we can say. What we can say, there are actually two theorems. So one is by Edelman, and I believe it's 79, though I might be getting my year wrong, is that BPP is actually in P/poly. So there are polynomial size circuits for BPP. And the key idea is what you can do is you can kind of hard code the randomness. And there's a theorem of Sipser gas, or I guess this is Sipser gas. I believe this is the 80s. I'm missing my year. Maybe 84. I'm not entirely sure. There have been a series of theorems by Sipser and then by Gas, and there was an improvement. And what this says is that BPP is actually contained in the polynomial hierarchy. It's actually contained in sigma 2. So BPP is equal to co-BPP. BPP is closed under complementation. And the reason is the 2/3, it's sort of, you can flip it. You can see that the definition of BPP, let me see where I have. The definition of BP time, it's entirely symmetric between these. You can flip accept and reject, and you can flip these. And so what you get is that BPP is closed under complement, and hence BPP is actually in sigma 2. It's called pi 2. Sigma 2 intersection pi 2. And these are theorems that I will probably cover in the next lecture. And so you might ask, okay, so what do we think about BPP? BPP seems to give a lot of power. BPP, because it's probabilistic polynomial, there are all these like interesting algorithms that we can get with polynomial power. We prove it's in the polynomial hierarchy, but remarkably, complexity theorists think that BPP is actually equal to P. they actually don't think that randomization gives you extra power. The reason for this is very deep. I mean, it's not just a random thought. So in some sense, here's this beautiful picture that we drew. What complexity theorists actually believe is that all of this is just P. They think all of this is the same as P. And the reason to believe this is this was by seminal work of Nissan and Vigdusson, I believe 94. I could be getting my years wrong over here. Maybe it's later than that. Where what they actually okay, so the statement of the theorem is more complex, but I'm going to write essentially an incorrect version of it, which is an imprecise version of it, and let's just flow with that because that gives the basic idea. So what they kind of said is, if SAT does not have a circuit family of size 2 to the epsilon n. So if SAT really needs an exponential size circuit family to solve, which is kind of what we believe. What they have is an assumption which is somewhat different from this, and in some cases it's actually weaker. I mean, they don't need to do it with SAT, they can do it with certain other languages, but let's not go there. Essentially, they're saying if SAT does not have a circuit family of size 2 to the epsilon n, so there's some epsilon, for some epsilon, for some epsilon. Which means if SAT doesn't have small circuit families, because 2 to the epsilon n, it's still exponential, but it's less than 2 to the n, right? It's still non-trivial. Then P is equal to Bpp. So what they say is, if you think that SAT is really hard, then you can use that to prove that P is equal to Bpp. Which is sort of remarkable. And the connections through this is a beautiful series of connections, and this is referred to in the literature as de-randomization. What they said is that Bpp can be de-randomized. What this means is, you look at the random tapes there's a random tape. You can actually simulate the random tape by something that is efficient itself. So you can construct something that's actually really... So let's think of it this way. The problem with simulating all the possible randomness is there's a polynomial amount of random bits, and therefore it's exponential time to simulate all the random bits. What they're saying is you don't really need to simulate all the random bits. You can just simulate a few carefully chosen seeds, and that's enough to determine whether it's going to accept with probability 2/3 or 1/3. So this is called de-randomization, or indeed what they say is that circuit lower bounds imply de-randomization. So what this says is, if you can actually prove circuit lower bounds, which we believe, this is what a circuit lower bound is. It's sort of saying that this is kind of like saying that NP is not in P/poly. Although the technical definition is different, but this is one way to look at it. That it's kind of like that. So saying if NP is not in P/poly, again, this is not exactly what they have. What they have is somewhat different. Then P is equal to Bpp. So this is saying circuit lower bounds imply de-randomization. There is a series of work which does the opposite, which remarkably says that if you de-randomize, that implies circuit lower bounds. So this is Impagliazzo and Cabinet's is one example of this, and this I believe is maybe it's like 04 or 05, and then there have been more results along these lines. So what it shows is that this notion of de-randomization, which is saying that Bpp is P, and in some sense the primary challenge of complexity theory, which is to prove circuit lower bounds, or to prove lower bounds, to show P not equal to NP, these are actually related. So this is almost like saying that if P is not equal to NP, then P is equal to Bpp. So these are two beliefs that you might think are like, you might think that P is not equal to NP and P is not equal to Bpp, because it seems that randomization gives you more power, non-determinism gives you more power, but remarkably, if you think non-determinism gives you more power, then randomization does not give more power, at least with respect to polynomial time. Unfortunately, the proofs of these are beyond the scope of this course. One would probably need another course where we could cover these results. So this is sort of some summary of Bpp. The kinds of theorems that I will likely cover in the next lecture are Edelman's theorem and Sipser-Gass, which we can definitely do in a lecture. But it's important to know that even though the only thing that we can prove is that Bpp is in the polynomial hierarchy, we actually think that Bpp is equal to P. I want to emphasize, it doesn't mean that randomization gives you no power, right? Randomization can help you, but within polynomial time, it's not going to give you more power. Maybe it's quadratically faster. Maybe it's quadratically faster. It gives you some kind of polynomial improvement. But what it says is that it will not give you any efficient algorithm for a problem that is not in P. And indeed, going back to primality, this is one of the reasons why it was believed that there was a polynomial time algorithm for primality, because we believed that P is equal to Bpp. And what has happened is that over and over again, various problems that were in Bpp or RP or co-RP have eventually been shown to be in P, but not all problems. I mean, if you did all problems, then you're doing de-randomization. And there are certain canonical problems for which it has been a struggle, and it is known why it's been a struggle to get deterministic algorithms. But for many other problems, de-randomization has actually happened for specific problems.
There are Bpp complete problems?
It's a good question. So actually, it is unknown if there are complete problems for Bpp, and the reason seems to be that it's hard to sort of syntactically define. Bpp has this sort of strange, like for all the other languages, you can kind of syntactically come up with a complete problem by some kind of padding. Right? For NP, you would basically say, like, take a Turing machine, put the running time in unary, and that becomes a complete problem. That doesn't work for Bpp.